Hello, brief calculus students. Integration using substitution when you have functions in the exponents. We'll be looking at the derivatives of exponential functions, but they'll just kind of guide the substitution. First of all, the derivative of e to the x is e to the x, and so nicely, the integration, the indefinite integral of e to the x dx is e to the x plus a constant. When we have derivative a to the x, we have natural log of a times a to the x. So when we integrate a to the x dx, we get 1 over natural log of a to the x. Or if we have that natural log already in the integral times a to the x, we just get a to the x plus c. So if you have it in the integral, you don't need it in the derivative, or in the solution. If you don't have it, you've got to have the derivative. Same thing if you have a constant times this, the constant just comes along for the ride. So it's either going to be similar, just times b, similar to the first situation, or b times where you have the natural log. That should not be a fraction. Okay, fixed. Natural log times, so it's already there, then we just have the derivative of b times a to the x plus c. So knowing what the chain rule looks like helps us with U-Substitution. So this is from an older video. We have the derivative of a constant times another constant raised to a power. We make sure we have the derivative with respect to that power. So if we have the integration, we're going to have that a to the power comes along. So for example, this was derivative 2x minus 1 equals the natural log of 2 times 2x minus 1 times 1. So it was chained together. So when we try to take the integrand of 2 to the x minus 1 dx, we know we're going to have some extra pieces. Step 1. The U-Substitution starts with u is the function in the exponent. Step 2. Find the derivative of u. Step 3. Do you need to solve for dx? Basically, we just have dx, and sometimes when we take the derivative of u, we have extra numbers or terms around. In this case, we just have dx, and du equals dx, so we don't need to worry about trying to get dx by itself. Step 4, substitute in u and du, and then solve. So this becomes 2 to the u du, that substitution. And using this, we know we need 1 over natural log of 2 times 2 to the u power plus c. So step 5, let's replace u with that x minus 1. It'll give us 2 to the x minus 1 divided by a natural log of 2 plus a constant. So taking a little differently, where we have the natural log in the integrand, and using the example that derivative of 3 to the 4x power is the natural log of 3 times 3 to the 4x power times 4, because that's the derivative of 4x. So a similar situation, integrand. So we've got the natural log of 3, and we've got 3 to the 4x, and looks like we're missing the 4. So let's see what happens. Step 1. Let u be what's the exponent. So not the ln of 3, not the 3. It's got to be what's in the exponent. 2. Find the derivative of that u. In this case, it's 4 dx. Just move that down a little bit. 4 dx. So, do you need to solve for dx? Dx is by itself here, and it's not here. So, what if we divide both sides by 4? end up with dx equals 1 over 4 du. So when we replace this in for dx, we've got to make sure we get that 1/4 du. So substitute in, that's going to be u, and this dx changes to 1/4 du. So looking at this, we're going to get to our probably 3 to the u plus c. We've got that 1/4. So that 1/4 just comes along, it's a constant. 3 to the u plus c. So let's replace u, which is 4x, which gives us 1/4 e to the 4x plus c. Alright, so a little bit harder one where the exponent is quite the function. I didn't make it into a... This problem could have been much harder, but I left the 2x in here for a good reason. So even though it looks like two functions, it's still an exponential function right here with its derivative, or the derivative exponent. So if you use the exponent, so that's x squared. It's not the 2x, it's not the dx, it's the exponent. Then we take its derivative, we get 2x dx. Then do we need to solve for dx? Do we need to change this to dx? In this case, the 2x and the dx are already there, so we can just substitute du in there. So it'll just be 10 to the u times du, which is equals 1 over the natural log of 10 times 10 raised to the u power plus c. Then we substitute back in for u, and it's just 1 over natural log of 10 times 10 to the x squared power plus a constant. Okay, last example. The derivative of 2 times e to the 3t is 2 times e to the 3t times 3, because we take the derivative of that 3t. Constant just comes along for the ride. So what happens if we want to take the integral of 2e to the 3t? So it looks like we've got that first part of it, we're missing that 3. I can always pull a constant out in front, doesn't matter. Okay, first step, the u is going to be whatever the function is in the exponent. In this case, it's 3t. Then du will be 3 dt. We're just looking at dt, so let's solve for just dt and get 1/3 du equals dt. So we're going to substitute that in. 2 times e to the u times that 1/3 du, because that's what we needed. Which is, I just pulled the 1/3 out and made it 2/3. So 2 times 1/3 is 2/3. E to the u, and simple piece of cake. 2/3 e to the u plus c. Substitute the u back in and get 2/3 times e to the 3t plus c. And we're done.